And I'm planning on keeping it until, I don't know what happened to me to put it down. So you can use a QR code to get to the link. Or if you want, email me, I'll send you the link directly. But what I will be talking today, shameless advertisement, it will be basically the two papers I participated in. But what I wanted to point out is that this special issue of the New Journal of Physics, it was, I turned it on. So it was actually very special. It was a very unusual design that it was all tutorials, and it was designed for for people who maybe want to start this type of experiment. So it is all about hot vapor experiments, but you can imagine that there is a lot of useful information in general. But the way all the articles are made is that they give you kind of the basic information about whatever project it is. So for example, one of our paper was about EIT. So it has all this derivation about EIT. And then there was a kind of the overview of some of the things which are special for hot atoms EIT. And then at the end of every article, there is basically kind of a recipe. If you want to start this experiment, what you should think about. So it's really an excellent resource if you just want to learn about any of the topics. And again, these are the two papers I participated in. They have something about 10 terahertz imaging, something on rubidium spectroscopy, and all other things. And all of it is open access, so you don't have to pay or have a subscription to go to it. All right? OK, so let's start the lectures. So last time, we discussed that if we're trying to build the sensor, there are many reasons why just to having two-level system may not be the greatest idea. OK? So how we're going to solve this right now is to go to the two-photon resonance. So today, we mostly will be talking about two-photon Raman resonances. Okay? So in this case, as I kind of indicated yesterday, we will be talking about three-level system, which will have one common excited states and two ground states. And depending on your experiments, there can be two hyperfine states, two Zeeman states. And then you can very easily translate the same math if one of those states is actually upstairs, if we need to. So now, of course, we will also have two optical fields which interact with the two transitions. OK? And for each of those fields, we will have its own detuning. OK? And again, just to specify, so delta 1 will be detuning of the field 1 from the resonance AB. And the second one, correspondingly, will be detuning of the second field from this optical transition. OK? Now, we can write down the Hamiltonian for this three-level system. Again, I'm going directly to the rotating wave approximation, because why not? So in this Hamiltonian, looks like this. Delta 1, 0, minus omega 1, 0, delta 2, minus omega 2, minus omega 1 star, minus omega 2 star, and 0. OK? Now, in the calculations, having kind of fairly large one-photon detuning always makes things harder. So for a lot of kind of easy explanations, we're going to put a detuning to 0. And because I know it is morning, so we're looking at the resonance case, let's rewrite this Hamiltonian for this resonance condition, because it's easier to find what is so special about it. OK. So now a little exercise. My claim is that we can look at the eigenstates. And this Hamiltonian has one very special eigenstate, More specifically, it has the eigenstates, which is non-interactive. So the eigenvalue corresponding to the state is 0. Let's do a little algebra exercise. Work with the people next to you and figure out what is the actual expression for the eigenvector corresponding to this non-interacting state. Go ahead. I know it's early. You need to remember how to do eigenstates. All right, how are you guys doing? Anybody got it? Okay, I'll give you a little more time. And I probably should say that this is like B, C, A states. All right, hopefully you either got there or you're very close, I'm sure. So if you go through, you will find that the eigenstate, which we will call dark state, have the following form: omega 1, state C, minus omega 2, state B. And for normalization, we add omega 1 squared plus omega 2 squared. Anybody got this? Good. So what do you think is special about this state? Say it again? There is no energy, which we can also transform. It doesn't contain any of the excited state, right? So what it means is that if the atoms are in the state, remember, these are two very long-lived states. So atoms are going to stay in those two ground states for, well, as long as we basically care to keep them. And this is the excited states, which are our lossy state, where spontaneous emission take the energy away from the system. So that means that if atoms are in a dark state, they basically do not interact with light anymore. Okay? So this is really a non-interacting, long-lived state. And this is clearly a win-win, because you can always, for any configuration for this lambda system, you can find the dark state. But if the states are decaying, that's not going to help you much. Okay? So in principle, if the atoms are in the state, they stop seeing whatever light field we're sending in. And we will see that this is kind of the basis for electromagnetically induced transparency, which, again, I already talked, I gave you the spoiler yesterday, so you kind of know where we're going to. Okay, but Remember, we did that for a very specific case where detunings were the same. Now, if you go through a slightly more complicated algebra, you can show that this state exists for any delta 1 equal to delta 2, or we're going to define the two-photon detuning delta, which is the difference of the two. Okay? So that corresponds for the delta equal to 0. So two-photon detuning is equal to 0. And here, basically, I'm going to kind of look at the two different situations. First, how far the lasers are detuned from the excited states. And then, what is the difference between the frequencies of two lasers and the ground state transition? Because essentially, what I'm doing with this two-photon transition, I'm creating the link between the two ground states using the optical fields. In principle, I can use a microwave field to access it. There's nothing wrong with that. But I want to do it optically. And to do it optically, I need a link of the two photons. Okay? Now, this is, of course, a kind of very special thing. Like the beauty of it, we'll see that it's actually way less dependent now of the one-photon detuning of the light. So we mostly care about the two-photon detuning. Now, of course, this is the very special point. What's going to happen if the two-photon detuning is not exactly 0? So in this case, the dark state is going to basically evolve in time. And the way it's going to evolve in time is that we're going to have, let's say, omega 1. Let me call this factor omega, because it's just a normalization condition, times c, minus omega 2 times omega e to the minus I, two-photon detuning times time, state B. Okay? So basically, and you can show it explicitly from the Hamiltonian. So we can see that now the phase between the fields start changing. You can already see that here because there is a specific sign between the two states. It's a coherent superposition of the ground states. So basically now this coherent superpositions start to drift. Why it's good or not good? Well, we can look at the dark state. And as I said, we're basically taking our system and we're transforming it into another one. So we rotate our ground state. So let's say we keep our excited state the same. And now we discovered that one of the ground state combination is our dark state. Now let's find its orthogonal component, right? So what is the other basis? It's called the bright state. That's already can give you the idea of where it is coming from, where we're going with that. And it's very easy to look at this dark state and figure out what state is normalized and orthogonal to it. So the bright state is omega 2 omega, state C, plus omega 1 omega, state B. Now, if we go back to Hamiltonian and rewrite it in this new basis, what we will discover is that originally we had the two of these optical fields interacting with our two transitions. In the new basis, there will be no optical field interacting with dark transition. So all the interactions will happen between the excited states and the bright transition. So essentially, if we have an atom in the dark state, it's completely oblivious about the light. So it's not going to absorb any light. So that means that the light travels through. It doesn't even know that there are atoms present, right? So however, if the atom is in the bright state, it's very eager to interact with light. And therefore, some of the population will be moved to the excited state, depending on how strong your optical fields are. And that's where we're going to get losses. Okay? So now we can look at this kind of time-evolving state and do a little bit of algebra. So we can write it down as 1/2. And I will write down state C. And actually, OK, let's do things a little easier because it's early in the morning. So for this particular calculations, I will put omega 1 equal to omega 2 equal to 1 over square root of 2 of omega, because it's just easier this way. In this case, you can see that the dark state is just a basically difference of the 2 states, and the bright state is a sum of them. Okay? Again, you can do it fully. It's just a little more of math. So in this case, we look at our dark state over here. And if we start evolve it in time, now I'm going to replace this as 1 over square root of 2. State C is going to be the dark state plus bright state over square root of 2. Then the state B is going to be the bright state minus dark state over square root of 2. But now, if it's involved in time for non-zero to photon detuning, we also have this factor minus I delta t over here. And again, it's delta times t. It's not delta t. And then, of course, we can make the transformation that is going to be 1/2 bright state 1 minus e to the minus I delta t plus 1/2 dark state 1 plus e to the minus I delta t. And therefore, if we combine it together, it's going to be sine of of delta t over 2 times the bright state plus cosine delta times t over 2 times the dark state. And then, of course, there will be a common phase factor e to the minus I delta t over 2. But we don't care about common phase factors. Okay? So now I think you can easily see what is going to happen. So time equal to 0, we are in a dark state. But as the time progresses, you basically start rotating from the dark state to the bright state. So what we expect that we start in the dark state when the atoms are not absorbing, and the more time passes by, the more likely the lights to start get absorbed. So what I'm trying to show is that we're going to have a transmission resonance at delta is equal to 0. Now, how wide this resonance is going to be? Basically, it determines, you can see that when we acquire the phase of about pi, we go exactly from the dark state to the bright state. So we can say that when delta times time is around pi, more or less, that's where we lose all these fun coherence effects, all the transparency effect. So the question is how long we can let the atoms to progress. So in this case, there is a question of how long we can keep them in a dark state, even if it's precessing. So that means that the widths, so let's say that the widths of the transparency peak will be approximately pi divided by the lifetime of the dark state. The good thing about that is that, remember, the dark state is combined only from the spin states. So these are long-lived states. So in principle, this lifetime can be quite long. And that means that the widths of the resonance can be quite narrow, which is good. So there are some experiments where people have achieved a seconds of the ground state coherence lifetime. You kind of have to work quite hard about that, or you can have vapor cells with quite excellent coatings, so the atoms can actually move around for a very long time, keeping their coherence. But it is possible. And even for a lot of kind of regular type experiments, this can be done in the order of like approaching milliseconds, which means that you're approaching kilohertz resolution on your resonances, which is, again, you remember we compare to the cold atom two-photon resonance is like 6 megahertz, or if you go Doppler resonances is like 400 megahertz. So we already can do things much, much better than before. Okay? So this is kind of a qualitative throw-in how EIT, well, I haven't told that this is called EIT, but this is called electromagnetically induced transparency. Okay, any questions so far? Okay, so now we're going to look at this as in a little more details. And so how we're going to do that, we can look at this Hamiltonian, and we can write down the Liouville equations as we do. Okay, let me go down here. So here I'm too lazy to write them down on this board. Unless you really want to, I don't know if you really want to copy them. This is in this first article I have on my reading list. And it's basically just tell you what are the density matrix calculations for this thing. So here again, if we're doing the exact calculations, and I can tell you that for EIT, you really need to do density matrix if you include the decays. There is no shortcuts over there. But you can see that we have the decay rates for the excited state populations and for the ground state populations. Sorry, for all the optical coherences, and we're going to keep track, of course, of the optical coherences for the spin states, which will be here, row 1, 2, or in my notes, I'm sorry I didn't use the 1, 2, 3 for the states, but A, B, C, so it's row BC. And the optical populations are AB, and CA, okay? Now, of course, you can put these equations in the computer, and you can get exact solution for any detuning and any strengths of the optical field. It's not even that hard, but expressions are like a little clumsy. So for many experiments, people are working in a very specific regime where one of the fields is strong and one of the fields is weak. So more specifically here, omega 2, it's called the control field, and this is a strong field. And omega 1, it's the probe field, and it can be as weak as quantum few photon fields. Okay? And if we make this assumption, we can actually solve these equations much easier, and we can see some of the interesting kind of behaviors on the system. So let's assume that. And for this solution, we basically need to make the zero approximation about what are the coherences, the populations in this system to specify. Again, early in the morning, let's wake up a little bit. So what would be a zero-order approximation for this specific case? So we can actually guess the populations of the 3 levels pretty well. And what is the coherence or the control field transition? Again, I think it's an excellent exercise to talk to someone next to you or around. What do you think the answers are for those? For, again, zero-order approximation, where our omega 1, the probe field RIB frequency, is a small parameter compared to omega 2 or control. Okay? So discuss. All right. I hear the voices are kind of slowing down. So what do you guys think? What we can say about these values? Yes?
What is R?
R, which R? Sorry.
The first line. The first line.
Oh, okay. This is the, yes, this is the pumping in this, like it's the atom entering the system. But you can kind of forget about this for it now.
It might be population difference, like rho 3 minus rho 1.
Yes, so this will correspond. So these are the exact equations. Sorry, I didn't explain that. So in moving vapors, or in any case, you may have atoms leaving your system, and then they have to enter. So this R terms, this is the rate of atoms entering the system. So, but I think, again, for this exercise, you can assume that it's a very small parameter, so the atoms kind of hang around. Okay? Any comments, questions, suggestions of what are the populations of the states are going to be? So actually, how the zero what would be, again, if we assume that the omega-1 is much smaller than omega-2, and we're looking at the kind of zero-order approximation, what this zero approximation is going to be? How the system is going to look like? Slightly louder? Yes. So what is going to happen is basically, what is the zero approximation? It's when your small parameter is just 0. So that means that we will be in this situation where we have C, B, and A. And basically, you only have a strong optical field acting on this resonance. OK? So then what can we say? So you already said that all the population will end up here, right? So we can say that rho 1, 1 is probably will be 1. That's a good guess. What about the other populations? They're going to be 0, exactly. So these states are basically going to be empty. Okay? So, and we have only one more. So what do you think we can say about the optical coherence on this resonance? It's also going to be 0 because, well, there is no atoms. Nothing happens. So that's exactly what I should have here. Yes. So if you got it, very good. And this is make our life much easier. Because now we can say that a whole bunch of terms are going to disappear from here. And that's also why we're not going to see any absorption for the control field, but it's kind of like we don't expect any absorption for the control field. On the other hand, we just discussed that we will have the transmission resonance. Remember, all the atoms are going to be in the ground state 1, or in the ground state B in my notation. So you have all these atoms there, and yet you will see that you still have no absorption there. So that's kind of why electromagnetically induced transparency was this kind of cool thing, because you can have, the atoms are still there. They just happen to be in a quantum superposition, which you don't interact with. Okay, so this is kind of one of the exciting things about EIT. Now, if you look at this in these levels, and you, again, you make this approximation, we can see something very interesting. And again, I will be using kind of generalized decays, which includes both decays of the ground state coherence and the optical coherence for the probe. And they contain the detuning, 2-photon detuning and 1-photon detuning. But in this case, we can find that gamma BC, so generalized decay for the spin coherence, times the spin coherence CB, equal to I control field Rabi frequency times rho AB, which is the optical coherence on this transition. So now we're adding kind of omega probe over here. Okay. Now, I'm not going to talk about kind of quantum side of EIT here, but I just want to show you that, look, we're writing this in a semi-classical approximation. So of course, we're talking about mean field density matrices and populations and coherences. However, I can do exactly the same thing, and instead of Rabi frequency, use the atomic quantized spin wave in atoms, and I can use quantized atomic states for the field. So this is basically will be polarization of the optical field. And what this equation really tells you is that now we can have a connection between the quantum properties of optical field on the probe transition and the quantum properties of the spin wave in the atoms. And this is really the strong coupling between the optical field and the spin field, which is the basis for EIT-based quantum memory or many other Raman memories, okay? Because this connection works on the classical, on the quantum realm as well, okay? But for us, it's just a convenient thing. So, and again, for the quantum memories, again, I had a long history working with like stored light before, so that now you can basically take whatever your probe field is doing, and you can map it into the spin waves, right? So you can have it over there, and then you can read it out, and that's how the quantum memory works. Okay. Anyway, so now with this, we can put in numbers in the equations, and we can find that again, I will use, for simplicity, I will put delta 1 equal to 0. It just saves times a little bit. In this case, the gamma AB is essentially just gamma AB. I will still keep the delta, the two-photon detuning, but I assume it's very small, so it doesn't really affect. So I will assume that delta is much less than gamma AB. So I can simplify that. So in this case, we can find that rho CB, so the spin coherence, is equal to minus probe frequency, Rabi frequency, control frequency, Rabi frequency, divided by gamma BC, divided by gamma BC plus omega C, omega control field square over gamma AB, minus I two-photon detuning. Okay? So this is, again, this is the spin coherence between the two ground states. Now, if you look to the notes from yesterday, we did look at the two-level system and coherence in the two-level system. And then when it had expression kind of like this, rho BA was I omega gamma AB plus I delta. And then there was, of course, the term for the population, so on. But what I want to point out here is that you can see the similarities between these two terms. So for example, now instead of just a one Rabi frequency, I have this two-photon Rabi frequency, effective Rabi frequency working here. And then instead of the width of the transition, of the optical transition, I can have this spin width with, and you can already recognize that will be the signs of the power broadening from your control field. We cannot avoid those. But what is important is that now we create this coherence and we read out this coherence, again, all optically. And we can see that, again, so for the two-level system, it's a kind of, we have an effective two-level system where the decay for this system is now becomes this new one, which is affected primarily by the spin coherence. Okay? Now, if we continue the calculations, okay, I'm going to erase this. And we take this expression for gamma CB. We can calculate the optical coherence, rho AB, which will be I omega probe, gamma BC, divided by gamma BC, gamma AB, plus omega C squared. Again, notice that because we make in this approximation that the probe field is weak, this is a linear expression. We don't have any nonlinearity connected to the probe field. It's not necessarily the case. We can solve the system with a stronger probe, and things will be different. But again, remember, this is our optical system, so we can calculate the susceptibility. as n dAB squared h epsilon naught rho AB divided by omega probe. So it's the same expression as we had before. And if we substitute everything in, we will have I n dAB h epsilon naught. And here we have gamma 1, 2, gamma 1, 2, gamma 1, 3, plus omega c squared. Okay? So this expression is true for any tunings. It's only assumed that the probe field is weak. Okay? So here we will have to, we first look at the two kind of critical cases. One is we have a resonance case. And this is kind of what we were playing with up to now, where the detuning is close to 0. We can shift a little bit, but it's basically on top of the optical resonance. In this case, the susceptibility, again, it's mostly, we assume that it will depend on the two-photon detuning. And it has this expression. Let me write it down. I 2 alpha naught, the definition of unsaturated absorption from last time, divided by the wave vector for the probe field. And then we have something like this, gamma AB times gamma of EIT plus delta square. And I will just say that, OK, I'll be effective. I will define gamma EIT as this. All right, so this is the width, the characteristic width of our resonance. So here we have delta square. And this is a kind of imaginary part minus real part minus I delta. And here we have omega control squared divided by gamma AB. And in the bottom, we have gamma EIT squared plus delta squared. Okay? So you can already see that this part, because of this I, this is the imaginary part. And this is a real part. So this one will correspond to the absorption. This one corresponds to the dispersion and refractive index. So ultimately, we will find that the absorption for the probe on close to EIT resonance is equal to alpha naught gamma IB times gamma EIT plus delta square divided by gamma EIT squared plus delta squared. Okay? Yes? Yes, so from now on, we're only looking at the probe field because the control field is so strong, it just goes through. It's important, we really need it, but the optical properties for this field are basically unchanged compared to vacuum because there is actually very little atoms on this transition. Again, it might change if the fields becomes more equal, then you will need to kind of do more calculations, but it's along the same line. You actually will see EIT in any case. Sure, okay? So now what it means is that if we look at the absorption, now I'm not really showing this here, but of course nothing is going to happen with our normal broad absorption, like one photon absorption if we look at delta. But when we have our delta close, the two photon detuning close to 0, we will find a very sharp transmission peak. Now, how sharp it's going to be, if we compare the absorption on EIT for delta equal to 0, so if we're sitting on top of the EIT resonance, and we compare to the absorption for the, without EIT, basically, for the two photon atoms, we will find that it is basically equal to gamma EIT over gamma AB. I'm not showing calculations here, but it's in the paper. So now, as I said, gamma EIT is basically limited by the decay rate of the ground state coherence, of the spin coherence. So this number can be very small. Now, we talked about power broadening and how sometimes it's not great. We do have the power broadening here as well. But notice this is a control field, right? And it's a ratio to the optical transition. So in this sense, we can mitigate it. So we can choose our power of our control field where it's strong enough so it saturates the transition, but it's still comparable to the lifetime of the spin states. And therefore, as I said, we expect this thing to be tens of kilohertz, few kilohertz. If you're really ambitious, maybe a few hertz. And this is many megahertz involved. So that's why we can get a fairly high population. It also tells us is basically how the quality of our EIT, the height of our EIT, will be better if we're able to keep the atoms in the dark state as long as possible, which is kind of expected, right? OK, so now this I can calculate here. It's kind of a nice and simple. What is going to happen if we start introducing the one-photon detuning? So basically, we take our lambda system, and we start shifting the frequency away from the resonance. What we're going to see in this case, I will just show this is exact solution, is that the resonance start changing shape. So the black line over here, that one corresponds to the being exactly on top of EIT. And this shows that this is absorption. So we have some of the normal resonant absorption. And in the center, EIT destroys the absorption. So we have the peak down. However, now, if we start moving away farther from the resonance, you can see that the resonance becomes transformed. And if you look at the red one, that's the where you 1.5 of the radiation width again. So you're kind of on the outskirts. You can be on the outskirts of the resonance. Then we see something interesting. So basically, your picture transforms into having one resonant absorption peak, which we kind of expect because we have atoms there, and then one kind of sharpish peak. Now, this is actually, again, if you go far enough, it's again the case you can do nicely algebraically. So, and I can look at the expression for the susceptibility from here, because this is a general one, and I can rewrite it in a way that may illuminate a little bit about what's going on. And what we have here is I2 alpha naught probe field, gamma AB minus I delta 1 plus I2 alpha naught over Kp. And here we'll have omega c squared over delta 1 times gamma r minus I delta minus delta r. So these are the two general parameters we introduce. Here, the delta r is equal to omega c squared couples over delta 1. And we'll call it a Raman detuning. And the Raman width over here is going to be gamma BC. Plus, it's a little different. It's not just the gamma AT we had before. Gamma AB control field square over delta square. And this approximation here is valid if omega c is much smaller than delta. Okay? So we assume that we're far enough from the resonance. So let's look at this one. Does it remind you of anything? So this is susceptibility. Each of this resonance, maybe it reminds you of anything in a form. Yes, so it's a two-level systems, right? So basically, we have distinct two-level systems. So this is, if I hide this one, This is basically exactly the two-level system for the probe field. And this is exactly what we see on the kind of remaining absorption. So if you take your laser, and even if you have a control field fairly far away, you tune your laser for the probe transition, you see normal absorption. Nothing interesting here. However, in addition to that, if we actually bring the field, so again, now we're basically in this situation where we are far detuned, but our field are in a resonance with each other. So this is a large delta, but now they're detuned. But now we actually see an extra absorption peak. So we can see this very sharp absorption peak. And it's also look kind of like a two-photon resonance, except the Rabi frequency now is an effective Rabi frequency, which is control field square over the detuning. And then the resonance will be actually shifted away a little bit from the 0 to photon detuning by this Raman shift. So again, how are we doing in time? I think we're OK. So it's a really tough question, but I will give you a couple minutes to discuss, can you explain this? And I can give you a hint. Last time I mentioned the dress state picture. So try to think if you can explain this behavior using the dress state picture. If you don't know what the dress states are, remember that's when we mix the state and they have different energies. Try to find someone in your vicinity who knows what the dress states are if you don't. So I'll give you a couple minutes to talk about this to see should we really expect this behavior or not if we're thinking of the dress state. OK, any suggestions? How can we explain the presence of these two absorption resonances instead of our, in our system? Anyone brave enough?
I can give an intuition.
Sure, go ahead.
So, if I'm not mistaken, when we talk about dress states, we're talking about the dark and the bright states.
Mm-hmm.
Like hiding. So we're talking about the dark and the bright. And how I see it is that EIT doesn't really care about whether or not we're resonant.
Mm-hmm.
It cares about how close we are with the tunings with our program control. So for me, it feels like our dark state will be like moving with or the tuning. So then we will have this
Mm-hmm.
in our absorption, which is what moves the beat that we're seeing. That's like
Right. OK, so it's not 100% accurate, but there is a lot of interesting things in that. So the one thing which I forgot to, well, not forgot to mention, but I haven't mentioned yet, is that you can say, well, stop, we had EIT, and I just kind of tell you that if EIT should appear anywhere, it doesn't depend on one photon detuning, and you're talking about absorption resonances, where is EIT? Well, actually, EIT is still there. If you look carefully on the red line, do you see there is a point about 1.5 when the absorption dips down to 0? That's the EIT. So even if we detune far away, you will have a point where in ideal system, your absorption disappears. But the point is, if you're far away from resonance, it's not like you have a lot of absorption to begin with, right? So in this case, EIT becomes less noticeable. If you go from 95% transmission to the 100% transmission, well, great, but it's not going to be a very pronounced resonance. However, now this absorption peaks becomes much more noticeable. So what happened with the dress states here, if you remember that if we have the two-level system and we apply the optical field, we can basically put this in a black box and say, well, I don't know what's happened there, but if I probe it externally, right, I can find whatever the eigenstates of this interacting system are, and I have the two optical states, or like mixed states now, which are the dress states, right? And we had expressions last time, so I'm not going to repeat them. But basically, if we are far detuned, so our black box in this case is going to be basically strong control field acting between state C and A. But again, we can say, OK, this is the black box, and I just shine my probe field, and I see whatever the probe field sees. So for here, because we are far detuned, we will have the two states, but one of them will be mostly the A state. Let me write it like this. So it will be mostly the A state. So that will be mostly the normal absorption we see, the broad absorption, nothing interesting. But then there will be another state, which is kind of mostly the C state. And remember, this is a long-lived state, so that means that that's a narrow state. And of course, now, if we're trying to connect our B states, which either of these two states, this will give us the broad resonance with the characteristic decay of the A state. But this one will give us the characteristic decay of the C state, which is exactly why we're getting this very narrow absorption resonance. Now, I can tell you from the practical point of view, for the sensing, we really don't love Raman resonances. You can try use them. And the reason is exactly this intensity-dependent shift of the resonance, which means that if your control field is not perfectly stable or defect, that means your resonance is going to move around as well. It's usually not the greatest idea for the sensor, but it's certainly possible for some of the applications to apply that. Actually, a little bit of a fun. Now, can we use the same picture to explain EIT, the resonance case? Well, now in the resonant case, so in the resonance, the two states are basically equivalent. So that's going to be, it's kind of going to be our two states, and that's going to be like A plus C and A minus C. So they are going to be very symmetric. But one of them will have a plus sign, one of have the minus sign. So they have opposite parity. Now, if you have your probe field tuned exactly in between to them, it will have exactly the same amount of interaction with state plus and state minus. But because of this opposite parity, it's going to be the destructive interference between them. So probe fields say, OK, I'm not going to interact with either of you guys. You decide on your parity things. So that's why the absorption is going to disappear in the middle. Now, honestly, for myself, I never found this picture very intuitive. Like, OK, well, I understand this, but it's not going to help me to understand how the system behaves. But I think it's kind of an interesting way to look at EIT as a destructive interference of this kind of identical coherent superpositions. OK. And also where the dress state pictures becomes important is for, I think I mentioned yesterday, for the radio frequency detection for the Rydberg EIT. Because in this case, typically the way it's done, again, they're working with the two-photon EIT where they have not the lambda system, but they're going up this way. And the way they do the measurements, so this is the RF field they're trying to detect. OK? And the way the actual experiment is done is that this becomes our kind of black box. We have two Rydberg states, which are coupled by the RF frequency. So instead of the states, we see the dress states. And of course, now the optical fields are going this way. And what we see is that instead of like a normal EIT transition without, when we have no RF field, because we have these two fields now, we will see a splitting which is proportional to the Rabi frequency of the RF field. So this is how some of these measurements are done. This is, again, this is another way where the dress states suddenly find their appearance. Okay? Questions? All good? All right, so now let's talk a little bit about Hort atoms. So again, everything I said right now, it can work for everything. Now, as we expect, if we start moving things around, okay, let me erase this. If the atoms start moving around, we're going to have the same issue as before, that different atoms moving with different velocities are going to see different resonance frequencies. So because omega 1 is going to be different, sorry, minus k1 times velocity, and omega 2, okay? So that means the detunings, again, are going to be different. Okay, I'll just put like delta 1 and delta 1, and delta 2 and delta 2, just because I'm too lazy. And what is important, that the two-photon detuning, which is omega 1 minus omega 2 minus omega bc, you can show that you can write it this way. Now it's also going to be shifted, so it's going to be delta. This is the true laser frequency minus k1 minus k2 times v, okay? So you can see that here, we're also going to have the same problem. The different atoms are going to have the different things. Can we do something to help us? You can see that here we have vectors, which means that we might start thinking about the mutual orientations of the laser fields. And that's probably going to be the last exercise for today. But let's say if we have a lambda system, so we have one field going up, one field going down. That's how the two-photon detuning here. So how should I direct my laser fields in the experiment to minimize the Doppler effect? That's question one. So this is, actually I should say that this is delta for lambda system. And if I have a ladder system where my fields are going like this, in this case, my frequency will be a little bit different. It will be omega 1 plus omega 2 minus omega, if this is B and C, right? So that will be replaced with delta minus K1 plus K2 times V. So should we do something different with the orientation of the laser beams to help us? Again, I think it's fairly straightforward, but I'll let you guys discuss it for a moment. And you can tell me how I should arrange my experiment if I want to have the narrowest AIT to minimize the Doppler broadening in two of those configurations. All right, so the nice thing about this exercise, I don't even have to call anyone to give their opinion. You can show me. So if this is your two fields, how should you do that? So show me, how do you think, for the lambda system, how the two laser fields should be oriented to get the minimum. Yeah, very good. Now let's think more carefully. So what we want to achieve here. So if you want these two vectors to be subtracted, like if we subtract two vectors, how they should be oriented? I think they actually should be in the same direction. So most of people were showing me this, and I interpret it as the opposite direction. Okay, yeah, so first of all, they should be parallel to each other, because if you add the angle, that's kind of bad for everyone. And we also want them together in the same direction. So it's collinear configuration. And I can tell you from the practical point of view, that's kind of one of the killing weakness of the hot atoms. Because, for example, for quantum memories, there is a lot of advantages in the hot atom systems. But because everything should be collinear to work well, if you're trying to separate this few photon field from the very strong control field, it's hard. It's possible, but very hard. But basically here, we want a collinear configuration for the probe field and the control field. OK, what about here? Yeah, so here they really should go, again, collinear in the opposite direction. This is what we usually do for like a Raman field. The only thing that for EIT, because the wavelengths of this field are so close, we can actually cancel Doppler broadening for the two-photon transition almost to 0. And there are some tricks of how to make it really disappear. Here, for example, for the rubidium, the wavelengths is 780 nanometers and 480 nanometers. So it's a pretty big one. It really helps if we're doing a contra-propagating configuration. So majority of the Rydberg's experiments in the vapor cell, you will find that the fields are in orthogonal polarization. However, it's not going to help too much. And for majority of the experiments, people do still have, like the width of the resonance is still basically Doppler broadened. One of the experiments we're doing right now is trying to use the 3-photon EIT and bring the 3 fields at the angle such that Doppler broadening cancels out. Ask me next year if it works, because at the moment, some people say it's a great idea. Some people say like it's never going to work. So it's a quantum superposition. So we'll make measurements and I'll let you know. But this is, again, so basically how to beat the Doppler broadening. It's one of the things which we have to struggle all the time. Now, one of the things you may ask yourself, I'm sure you don't right now, but you may, is what's happened to EIT when we have the Doppler broadening ensemble? Because remember, we talked about how the shape of the absorption changes as you start to move away. So this is a really complicated way, but this is still the best way I know to explain what happens. So different colors here corresponds to the atoms moving with the different velocities. So you can, if you look kind of in the, and the top picture is kind of the zoom in of the bottom picture. So they kind of show in the same way. So if you kind of look carefully, in the center, there will be the resonances which are really create like a normal EIT resonances. This is for the atoms which are basically have 0 longitudinal velocity. And for them, EIT works exactly as we want. However, as we start moving further, you can kind of see how each of the resonance split in these 2 absorption peaks. And the one thing which is very important, which again we kind of mentioned before, is that there will be this one point for all of them on the 0 to photon detuning where we have the EIT, like true EIT. So that means that even if atoms now have a larger to photon detuning, they're all going to not absorb in exactly the same true to photon resonance. And this is what basically creates this narrow, sharp peak in the middle. So in a sense, for EIT point of view, sometimes having the Doppler broadening even better, because for the same amount of the control field, you actually get some of the narrowing because not all your atoms are exactly on resonance. Uh-huh. Right, because some of the atoms will be moving one way, and some of the atoms will be another way. So overall, it will be symmetric, because we assume that an equal number of atoms move. Now, if you originally have non-zero one-photon detuning, then actually the resonance will be asymmetric again, just like we saw before. All right? And again, I'm not going to go through this in many details, but just not to give the idea that everything is simple with the atoms. These are kind of the things we will need to take into account, depending on how much attention you want to pay what's going on with your atoms. So basically, what we did before with like averaging over the Doppler velocity, this is the one picture over here. So you just say that the atoms moving with different speeds, they have different detunings. You go and create your void profile, and you calculate what's going on. This is kind of the first step of taking into account the thermal motion of the atoms. For many of the experiments, because we want the atoms to stay in the dark state for as well as possible, we introduce some of the buffer gas. I think I mentioned it in my talk yesterday, is that we don't allow the atoms to just zip through your cell. We add some buffer gas, which creates this kind of diffusion. This diffusion itself may start affecting the velocity distribution. It may affect some of the collisional decoherences in the system. So in principle, that's another step we might need to include. Now, moving further in experimental details, our laser beams often have a limited volume inside the vapor cell. So that, and sometimes they have the same size for the probe and control. Typically, we keep probe smaller than control. Sometimes not, but there is a limited thing. So the atoms can travel through this. That will limit how long the atoms are going to stay in the dark state. Now, if you have a buffer gas on top of this, you may start creating some really interesting dynamics. When the atoms have their coherence, they move out of the beam, so they kind of diffuse out of the beam, but then they kind of diffuse back while they still remember their coherence. And that's why in some of the buffer gas situations, the EIT peak, instead of being like nicely Lorentzian, becomes really sharp, because you will have the contribution from these atoms, which are actually keeping their coherence for quite a long time. And for the sensing purposes, it might be good. It reduces your dynamic range, but you might be much more sensitive to any variation of your parameters close to that. And the final things, again, for some of the things, you might need to take into account what happens if you have the atoms in their coherences, and then they collide with each other or with the buffer gas, and their velocity changes. So that means that you have coherence prepared on one detuning, and then suddenly, atoms start interacting with the field on a different detuning. And for some of the experiments, it actually may affect the properties of the atoms quite strongly. So for example, during my PhD, that was one of the topics I studied for the nonlinear Faraday effect, is that the coherences created in two possible transitions had opposite sign. So if you have a coherence prepared on one of them, and then the atoms collide and change velocity and start preferentially interfering with another transition, well, they're screwed, because their coherence, instead of the dark state, becomes the bright state. So there was a very strong deep in nonlinear effect, which we end up describing. But in order to get to this explanation, we actually had to take into account on this. So when you're doing the calculations like this, there is a whole bunch of effects which you may or may not need to account for. OK, so in the remaining time, I wanted very briefly to kind of connect it to our sensors. So hopefully you have a little better idea what we're going to see if we realize the two-photon Raman resonances in our experiments. So how now we're going to use it for sensing? OK, so one thing is kind of obvious. We can track EIT peak position. So just we discussed before, if you have a three-level system, let's say you apply magnetic field, that's kind of more optimal for magnetic field. If your levels shift, that means that your two-photon detuning are going to change. So you're going to add some some magnetic dependent shift. So your EIT resonance is going to shift. So if you had your EIT somewhere here, it's going to shift by the amount proportional to the magnetic field. So this is kind of classical approach. How well we can do it. Remember, the parameters we pay attention to are essentially the width of the resonance in the amplitude. So how much better than the two-level system we're going to do? As we said, gamma EIT is gamma BC plus omega C squared plus gamma AB. So again, we will have to optimize the power of our control field. But here it's actually quite interesting because remember before, we had only one field. So you had the power broadening, and you cannot get a much stronger signal because of that. Because we don't basically depend on the probe field in our EIT profile, you have a little more freedom on choosing how much of the probe field you're sending in. So you don't have to sacrifice your signal up to a certain level. And I can tell you that in general, we're usually trying to optimize the widths to be, again, kind of the twice of the natural line widths of this transition. So for the sensors, the control field typically is not super strong, but you can see it's still strong enough to make your measurements. Okay? All right, but this is kind of the route we looked at. The only thing I want to mention is that in a real experiment, it's kind of hard to keep track of the peak. So usually instead of keeping track of the peak, what people are doing is they modulate the two-photon detuning or the frequency of one of the lasers. So instead of just looking at the frequency itself, you basically go up and down like this. Your frequency changes. And then, of course, you're looking at the variation of your signal at this frequency, right? So you're kind of taking a numerical derivative. So if your frequency changes, your signal is going to change. And for example, if you're on the side, you're going to have a very strong variation in one direction. If you're close to the top, your frequency changes like this. You're actually going to have very little oscillation on the same frequency. So if you look only at this frequency, you basically see 0. And if you're on this side, well, you can kind of see that it will be on the opposite side. So that means that if you look at, we call it demodulation. If you look at demodulated signal, it's actually going to look more like this. It's like a derivative of your slope. And of course, in this case, if you look how much your signal changes, you will be able to know how much your resonance shifted. So this is more of a technical thing. So another approach, which we may or may not use, depending on the type of sensor, is to look at the refractive index effect. So up to now, I was focusing mostly on the absorption. However, in addition to sharp resonance as absorption, we also have a sharp resonance in the dispersion. So for example, and again, the approach will be track refractive index. So we can go back to the susceptibility which I had for the EIT system, and we can see that the refractive index will look something like this. Alpha naught, 2 gamma AB over KP, some constant. And here we will have delta over delta square plus gamma EIT. Okay? So that means that if, multiplied by omega control square minus gamma BC squared plus delta squared over gamma AB. And for many sensors, we're staying with kind of a fairly high control field and very small detuning. So it's basically just this ratio. So why this can be fairly large if you want to. And this is a narrow resonance we're going to have. So that means that if we have a small variation in the refractive index, and we trace the variation, sorry, if we have a small variation in two-photon detuning due to magnetic field or electric field or whatever we are measuring, our parameter of interest, then that will induce the small variation in the refractive index, which is basically proportional to this two-photon detuning. So the way, for example, it can be realized in the experiment is, imagine we go back. Remember in the beginning, I had this kind of characteristic magnetometer three-level system. And we said that, OK, we have the connection between which spin states we are tracing with what is the polarization of light we have. OK? So for the magnetometer, let's say this one shift in the negative direction, this one shift in the positive direction. So that means that, for example, the refractive index for the sigma plus, again, -1, the variation in the refractive index will be in, let's say, if it increases, then the change in the refractive index for sigma minus will decrease by by the same amount. So if we have these two fields propagating through the ensemble, in principle, we can be pretty close to the top of the EIT resonance. As they go, they acquire the phase, which will be like change of phase for those will be basically Kp n plus minus times the lengths of our ensemble. And you can see that if we basically put all this together, we will find that it is equal to, 2 pi L over lambda p. That's the, how much phase they will acquire. And then depending on the polarization reflecting magnetic field, let's say, it will be plus or minus 2 gamma AB gamma EIT squared times delta. And again, this is the good ratio. We have the enhancement proportional to the difference between the radiative line width and the EIT line width over here. And again, nice thing is that if we're doing the phase variation, we want to use some sort of interference to get the signal out. So if I want to think as a theorist, basically what I want to do, I'm sending the linear polarized light through, which is the combination of sigma plus plus sigma minus. And then I'm going to separate them. One of them, let's say sigma plus goes this way, sigma minus goes that way. And then I'm going to connect them together. OK? And if one of them experiences one phase, let's say positive, and the other one, let me just like plus phi, and this one will correspond to negative, then when we combine them together, what is going to happen is the linear polarization is going to rotate by the amount of half of this phase shift. We can show it pretty easily. So that means that if I arrange, for example, the balance detection, where I can look at the rotation of the polarization, let's say if it's 45 degrees oriented, I will be able to catch the small variation in the refractive, in the magnetic field, and therefore refractive index, just by looking at the polarization rotation. So especially for magnetometers, this is a very popular way of doing things. So I don't think it makes sense, or else we have time, to go through actually various magnetometer arrangements. So for this, in this paper, which I put in, we tried to kind of capture how different magnetometers operate. And I think after these 2 lectures, you kind of can follow it. And I made this picture, so I'm sorry. We tried to go with whimsical and hand-drawn, but I have many talents. Drawing is not one of them. But historically, the very first, OK, let me try to be. Yeah. Does anything happen? Yeah. OK, I lose it very easily. I know it's somewhere here. OK, I see it now. OK, this one. So the first 2 magnetometers, they're called MX and MZ. These are kind of historically were the very first magnetometers. In a sense, they are the simplest magnetometers. They work on the optical pumping. Remember in the first lecture we said, if you send this circular polarized light, you prepare your magnetization. And in this case, essentially, we use RF field to flip this magnetization. And if you flip it, what it means for atoms, you bring the atoms back to the state which was empty, and therefore you see the absorption resonances. It works quite well, but it has a lot of systematic errors. So it's basically, it's probably more historical, although MX is still very much active magnetometer right now. This one is actually kind of interesting. Here, it's a first step toward going to all optical. So remember how we just said that if we go from the single photon transition to the two photon transition, it's kind of the way when you use the two photons to do the job of the one, let's say, microwave field. And here they're doing the same thing. The one fun fact, if you take the optical field and you modulate its frequency, it basically creates a frequency comb. So it creates several fields which are separated by your modulation frequency. And this is a trick we use quite often. And here, that's the trick exactly they use in the Bell-Bloom magnetometer, where you modulate your optical field at a frequency which matches your magnetic field. And this now two components will essentially be equivalent to the RF field, which will do exactly the same thing. Now, so these, the first three, they're kind of classical optical pumping magnetometry, where you first prepare magnetization, and then you see what happens. So the Hanle one, this is an interesting one, because now you use two optical fields. You use one strong control field, and for that one, you prepare your magnetization, and then this magnetization starts to rotate in magnetic field, but you look at this rotation using the weak probe field. And for this weak probe field, again, if you remember somewhere in the beginning, we said there is a big connection between the optical polarization and the spin wave. Now, if your spin wave start to evolve, that will correspond, that will be reflected in the optical properties for your probe field. And for this probe field, you basically start gaining very similar different phases. So you will be able to basically measure the precession of your magnetization looking at the rotation of your probe polarization. And the last one, nonlinear magneto-optical effect in EIT. These are the kind of a single effect, single laser beam configurations. So for NMR, it's essentially, it's very similar to EIT when you operate at the two circular polarizations. And in this case, again, just as we discussed, shifting the levels create the change in the refractive index and the polarization. And of course, the CPT-EIT magnetometer, that's exactly the first one I was mentioning, when you basically produce the bichromatic field and you track what kind of changes we see over there. And just for completeness, as I said, I spend a lot of time talking about magnetometers. But EIT is also very much in operational status for electrometers. And here, this is the kind of the actual example of how they use this splitting. It's called Altitude splitting, produced by the microwave field between the two Rydberg states. Again, in the dress state picture, we start splitting this resonance into two. And therefore, instead of like one nice peak, we have the two peaks corresponding to the position of the two resonance. And because in the dress state picture, the splitting is proportional to the Rabi frequency of fields, that's what we do. Another fun way people are using it more in Rydbergs than in, let's say, magnetometry, is to look at fluorescence. And in this case, if we have less absorption, I think I mentioned that in my talk, that means that you have less fluorescence since less atoms are in the excited states. But here, they actually use it very cleverly. So they use the 3-photon EIT excitation. And then they basically look at how much atoms are on resonance here by exciting them to some other state and looking at the fluorescence between specifically selected states. And then, of course, again, if we are on resonance, you will see less or more fluorescence. And in this case, of course, using fluorescence is really nice for imaging. That's the same reason why we're using the fluorescence for our Rydberg experiment. And then you can, I think the idea is that you can have a chip which has some terahertz field on that. And by monitoring it, you can basically read out what is inside this chip. Okay? So basically, to summarize today, we talked about how this type of sensors work. And tomorrow, on the kind of last third of these lectures, we start talking about noises and what we can do to use the quantum mechanics to potentially increase the sensitivity of the sensors. Okay? Thank you.